Okay, in this video I'm going to discuss about differential vector calculus. So for the vectors we have differential formats as well. So now I'm going to talk about the term of gradient. When it comes to differential vector calculus, we have this kind of terms. So now I'm going to discuss about gradient. So let's say that we have a scalar function. So let's say that we have a scalar function t, which depends on x, y, c. So then you can write this dt, infinitesimal change of t. So you can define this as partial differentiation of t with respect to x times dx. This is actually infinitesimal change of x. Actually this x, y, z are variables, so this can if you take that t is equals x squared y c squared, so this is this is my scalar function t. This depends on x, y, z variables. These are variables because whenever these are changing, so this t is also changing. So now if you say that this x is changed by an amount of dx, that is infinitesimal change. So let's say that y is changed by dy, so z is changed by dz. So now these represents the dx, dy, dz quantities. So now if you have the infinitesimal change of t, that represents dt. So dt can be written in terms of dabba t over dabba x. That means the partial differentiation of t with respect to x times dx. This is the infinitesimal change of x variable. So plus partial differentiation of t with respect to y dy, partial differentiation of t with respect to z dz. Okay, this thing comes from the differential calculus actually. So differential equation knowledge, from the differential equation knowledge, that you can write in this way. If you don't know how to write this way, I'll show it. I will show it to you. So since this dt can be written in terms of dx, dy, because these are the variables. So you know that if these are variables, so this should be dx, dy, and dz. Because when we have infinitesimal change of x and y and z, so these infinitesimal changes should be added to find the infinitesimal change of t. So that's why we are adding this. So these are actually unknown constants, like we have unknown constants like a, b, c. So we have to find the a, b, c to get this kind of equation. If you don't know how to get this, derive this equation. So that is why I showed you. Then I will take to find the a constant, what I'm going to do here is that I'm going to keep y and z as constants. So when we are going to keep this y and z constant, that means that dy and dz is equals to 0. So that means these terms will be cancelled out, and we will only have dt over, so this dt can be written as partial differentiation. This partial differentiation is equals to a partial differentiation of x. So that means that a is equals to dabba t over dabba x, because this only have when y and z are constants. So now likewise we have b can be this b can be written in as double t or double y when x and c are constant. So likewise we can derive an expression for the c. So we have this kind of equation for the dt. Okay, now you have seen that dt can be written in this way. So I'm going to do some interesting thing to this expression. So what I'm going to do here is that I'm going to I think I made a mistake here, so sorry. This is going to be dx and this is going to be dy, not y hat. This is going to be dz. So I'm going to do an interesting thing here. So I'm going to do double t over double x hat plus double t over double y hat double t over double c hat. I'm going to take the dot product with the dx x hat dy y hat and dc c hat. So so you have to think about this, why I have taken this. So so for the actually if you have x hat dot x hat dot x hat, that is equals to 1. So we will have double t over double x times dx. When we have y hat dot y hat, that means double t over double y and dy. So we are getting this when we expand this dot product, we will get this similar expression for the dt. So now if we take a look at this expression, so these actually there are two vectors. So what I'm going to do here is that if we take a look at that the last vector, so from the knowledge we have seen that r vector, this is the position vector. Actually position vector can be written in terms of x hat plus y hat and z hat. So if I'm going to take the dr, this is the infinitesimal displacement, infinitesimal position vector, or you can say the infinitesimal displacement vector. So you can write dx x hat dy y hat and dz c hat. So actually this represents the infinitesimal displacement vector, or you can say sometimes it can be considered as a position vector as well, infinitesimal position vector. For now for this actually we can have this kind of expression. So double over double x hat plus double over double y hat and double over double c hat t. So actually this is the dl vector. So you can say that dl is the infinitesimal position vector, or you can say infinitesimal displacement vector. So right now we have operator here. So this is called an operator. This operator has a name. So what's the name of this operator? So that is called as the del operator. So del operator is a vector actually. So del operator denoted as in this way. So this is called the del. So now we have the scalar t del t dot dl. So actually this gives you a what kind of quantity? This gives you a scalar product. So this is a scalar product, and the final result of this scalar product will be a scalar. So when we have this dt, so because the change of a scalar, infinitesimal change of a scalar, is going to be a scalar. So now when we come back to the del t, del operator of t, this this term has a special name. So this is called as the gradient of the scalar, gradient of t, because we are considering the scalar as t. So now this is the definition of the gradient t. So this is when we have a scalar, so the gradient of t can be represented as dA by x, so dA by t over dA by x, x hat, plus dA by t over dA by y, y hat, dA by t over dA by c, c hat. These x hat and y hat and c hat are the unit vectors. Okay, let's try an example here. So we have the scalar function as t is equals x squared by yc. So we need to find the grad t. Grad t means gradient of t. So, actually I have to talk about I have to mention that the gradient of t is called as the grad t as well. So now I'm going to find the grad t of this x squared yc scalar function. So first of all, I'm going to write the definition for the grad t. So this is going to be my definition. Del t or the grad t is equals dA by t over dA by x, x hat, and dA by t over dA by y, y hat, dA by t over dA by c, c hat. So now I have to find these terms, dA by t over dA by x, dA by t over dA by y, dA by t over dA by c. So I'm going to find them separately because that's going to be easy and more convenient, because it's not getting wrong. So when you have dA by t over dA by x, that means that you have to partial differentiate your scalar with the x with respect to x. So that means you have x squared yc, and you have to differentiate with respect to x. That means you have to keep other variables as constants. So these are the other variables y and c, so you have to keep them constant. So I'm going to take this yc as constant, so dA by x squared over dA by x. So this can be differentiated with respect to x, so that is going to be 2xyz. So likewise I have to calculate dA by t over dA by y. This is going to be equals to x squared c, and dA by t over dA by c can be written as x squared y. So now I have found all the terms that is required to satisfy my final answer. So I have this dA by t over dA by x, and dA by t over dA by y, and dA by t over dA by z. These are found actually. So now I am going to substitute them in this equation. So grad t is equals, so we have 2xyz for the x hat component. So now we have x squared c y hat and x squared y in the c hat. So this is my grad t, or the gradient of t. So I hope you understand the gradient. So in the next video I'm going to talk about the divergence. So I hope to meet you in the next video.